Projective Geometry, Volume 1, by Oswald Veblen and John Wesley Young.
Chapter 6, Algebra of Points and One-Dimensional Coordinate Systems. Section 59, Projective Correspondence between the points of two different lines. Hitherto, we have confined ourselves in the development of analytic methods to the points of a single line, or under duality, to the elements of a single one-dimensional primitive form. Suppose now that we have two lines L and M with a scale on each, and let the non-homogeneous coordinates in any point of L be represented by x, and that any point of M by y. The question then arises as to how a projective correspondence between the point x and the point y may be expressed analytically. It is necessary, first of all, to give a meaning to the equation y equal to x. In other words, what is meant by saying that two points, x on L and y on M, have the same coordinate. The coordinate x is a number of a field and corresponds to the point of which it is the coordinate in an isomorphism of this field with the field of points on the line L. We may think of this same field of numbers as isomorphic with the field of points on the line M. In bringing about this isomorphism, nothing has been specified except that the fundamental points P0, P1, P infinity, determining the scale on M, must correspond to the numbers 0, 1, and the symbol infinity, respectively. If the correspondence between the points of the line and the numbers of the field were entirely determined by the respective correspondences of the points P0, P1, P infinity just mentioned, then we should know precisely what points on the two lines L and M have the same coordinates. It is not true for all fields, however, that this correspondence is uniquely determined when the points corresponding to 0, 1, and infinity are assigned. Footnote: this is shown by the fact that the field of all ordinary complex numbers can be isomorphic with itself not only by making each number corresponding to itself, but also by making each number, a minus ib, correspond to its conjugate, a minus ib. It is necessary, therefore, to specify more definitely how the isomorphism between the points of M and the numbers of the field is brought about. One way to bring it about is to make use of the projectivity which carries the fundamental points 0, 1, infinity of L into the fundamental points 0, 1, infinity of M, and to assign the coordinates x of any point A of L to the point of M into which A is transformed by this projectivity. In this projectivity, pairs of homologous points will then have the same coordinates. That the field of points and the field of numbers are indeed made isomorphic by this process follows directly from Theorems 1 and 3 in connection with Theorem 1, corollary of Chapter 4. We may now readily prove the following theorem. Theorem 16. Any projective correspondence between the points of the pencil X and the pencil Y of two distinct lines may be represented analytically by the relation y equal x by properly choosing the coordinates on the two lines. If the coordinates on the two lines are so related that the relation y equal x represents a projective correspondence, then any projective correspondence between the points of the two lines is given by a relation y is equal to ax plus b divided by cx plus d, where ad minus bc is not equal to 0. Assumptions A, E, and P. Proof. The first part of the theorem follows at once from the preceding discussion, since any projectivity is determined by three pairs of homologous points, and any 3 points of either line may be chosen for the fundamental points. In fact, we may represent any projectivity between the points of the two lines by the relation y equal to x. By choosing the fundamental points on L arbitrarily, the fundamental points on M are then uniquely determined. To prove the second part of the theorem, let pi be any given projective transformation of the points of the line L into those of M, and let pi sub 0 be the projectivity y equal x regarded as a transformation from M to L. The resultant pi 0 pi equal to pi 1 is a projectivity on L, and may therefore be represented by x prime is equal to the quantity ax plus b divided by the quantity cx plus d. Since pi is equal to the inverse of pi sub 0 times pi sub 1, this gives readily the result that pi may be represented by the relation given in the theorem.
Projective Geometry, Volume 1. This book was written by Oswald Veblen and John Wesley Young. It was published by Blaisdell Publishing Company, London, 1910, and is now in the public domain. It is read by Jim Renhold, with programming and illustration by Jim Renhold, 2019. Thank you for listening.